Next, we're going to talk about summation notation. When the terms of a sequence are added together, the resulting expression is a series. A series is when you take a group of numbers and add the values together. This is a sequence, and you add them together, which turns it into a series. Series is adding a group of numbers together. It's finite because it ends. It doesn't keep going. There's no ... saying that the pattern continues. Finite, add your sequence together, so it's 2 plus 4 plus 6 plus 8. We're adding them, so it's called a series now. And this ... refers to it continuing on. You can use summation notation, what we often like to call sigma notation, to write a series. It's a shortcut. So here we're looking at the Greek letter sigma. This here is going to represent the 2 plus 4 plus 6 plus 8. We start with I equals 1 in the bottom. That means that you're going to plug a 1 into your rule to help you identify what the first number is. 2 times 1 would give you a 2. Then you pick the next whole number. 2 times 2 gives you 4. 2 times 3 gives you 6. 2 times 4 gives you 8. You keep going up, you keep plugging in numbers until you get up to this upper bound number, which is a 4. So that tells us 4 would be the last value we plug in. 2 times 4 is 8, and we stop. If it's an infinite series, we would plug in a 1 and a 2 and a 3, 4, 5, 6, 7, 8, 9, 10, keep going until we get to infinity, which of course we never would. So it just keeps going on. For both series, the index is, or the index of the summation is I. It's the letter I is underneath our sigma. I often like to use N. Sometimes you see the letter K. It doesn't matter what letter they use, they'll also use that letter in the rule. And the lower limit is the number 1. This is your lower limit. The upper limit of the summation, in this case, is 4 for the finite series and infinity for the infinite series. Summation notation is also called sigma notation because of the uppercase Greek letter sigma. We use sigma, the lowercase version of that, to represent standard deviation in an earlier lesson. Okay, we're going to write this series in summation notation or sigma notation. A few things you got to think about. First, you've got to know what the rule is. So to write our rule, we have to identify what type of sequence these numbers will come from. If I take the 7 and minus the 4, if I take the 10 and minus the 7, I get this common difference. So I know that this is arithmetic. So when we work with that, we're going to know that our first term is 4. Our common difference is 3. When we distribute this through, we get 3n plus 1. So that would be our rule. So we write sigma. I like to use n. when you write your own rules, it will typically have a 1 here on the lower limit. It's whatever value that's needed to be plugged into your rule to get your first number. So plug in your 1. 3 times 1 is 3, plus 1 is 4. And then we say 3 times 2 plus 1 is 7. 3 times 3 plus 1 is 10. And you keep going on. The question is, how many times do we need to be plugging in a number until we can get to the number of 46? Well, we can say 46 equals 3n plus 1 by subtracting the 1 to the other side. We're going to get 3n equals 45, and dividing by 3, we'll see that n equals 15. So we'll put a 15 on top of our sigma, called our upper limit. And there is your sigma notation. It has a rule, it has a lower limit, and an upper limit. You need the 1 to determine what your first term is. You need the 15 to determine what your last term is. Here, this is not adding the same amount every time or multiplying the same amount every time. So it's not arithmetic, it's not geometric. We often call that kind of a neither. It's neither one of those. So what's the rule? It's the position cubed that it would be in the denominator. So it's 1 over n cubed. So we take our summation notation, 1 over n cubed, and it looks like we have plus dot 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 telling us that it goes on forever, so we have our infinity sign on top. Over here we notice 14 minus 7 is 7. 21 minus 14 is 7. So we notice again that we have a common difference of 7. We're adding 7 every time. We have an arithmetic series. It's a series because we're adding terms together. So we're going to figure out what the rule is. So we have our 7 plus our difference, n minus 1, distribute, so our 7's cross out, positive 7, negative 7, and you're left with just 7n. Now to figure out how many terms you're going to have, we have 77 is our largest, with the rule of 7n, divide by 7, n has to be 11. So there's 11 terms in this series. So we're going to start with n equals 1. We'll use the rule of 7n, and it'll go up to 11. We're taking the term minus the term before it. Negative 12 plus 8 is negative 4. We have this common difference of negative 4. We're subtracting 4 every time, and that makes the numbers get smaller and smaller. That's why they're negative. Our first term is negative 4. Our difference is negative 4, n minus 1. Distribute, and we're left negative 4 and a positive 4 cross out with a of n equals negative 4n. It goes on forever because it has a dot dot dot, which tells us in our sigma notation that we're going to use the infinity sign for the upper limit. Now what can we do with the sigma notation? We've written them from a series. What if we just had them and we wanted to figure out its value? We wanted to evaluate what the sigma notation stood for. So here's an example of a sigma notation. It has a rule. It has a lower limit and upper limit. So we're going to look at when k is 3, when k is 4, and also when k is 5. We start out with the lowest number and we work our way up to our upper limit, which is our largest number. We plug the 3 in for k, we plug the 4 in, and the 5. This gives us 2 minus 9, 2 minus 12, and 2 minus 15. We're still adding these terms together. This is negative 7, negative 10, and negative 13. Negative 17 minus 13 more gives us negative 30. So we can say when k equals 3 to 5, 2 minus 3k is going to equal negative 30. On the next page, we're going to look at some special formulas for series and sigma notation. In this case, when you have your sigma with a lower bound of 1 and an upper bound of a number, we could say what that number was. If that number was 6, we would have 1, and we would add that to another 1 and add that to another 1 all the way up until we got to 6. 1 plus 1 plus 1 plus 1 plus 1 plus 1 is 6. We don't plug in a 1 plus 2 plus 3 because there is no variable sitting in the rule spot. They're just showing you here that the sigma notation equals whatever this top number is if your rule is plainly a 1. On this side, we have a sigma notation. I is 1. Your rule is I. This would be, for example, if you wanted to add the first 10 numbers of a series. You would plug in a 1, then you would plug in a 2, then you would plug in a 3 and a 4 and a 5 and a 6, maybe all the way up to 10, if n was 10. You could use this as a formula. Plug in your 10, 10 plus 1 divided by 2, and that would work out. Over here is the formula for adding the square of your position. It's a bit complicated looking, but it works out just the same. So here for a first one, this is showing us that we're going to be adding the terms 1 when you plug in a 1, and then a 2, and then a 3, and you would continue that pattern all the way until you got to 32. What is the sum of 32 terms? So, we're looking at the sum of the first 32 terms. So we're going to take our formula n plus 1, divided by 2. N in this case happens to be 32. 32 plus 1. That gives us 32 times 33. Gives us 528. Here, we're looking at a position square, but then we're minusing 6. This is not the sum of squares. Because of the -6. Okay, so in this case we can't use one of those formulas. We're going to need to write it out. We're going to need to write out the series. So we're going to look at when k is 4, when k is 5, 6, 7, and 8. So we're going to have 4 squared minus 6, 5 squared minus 6, 6 squared minus 6, 7 squared minus 6, and 8 squared minus 6. This comes out to be 10, and because this is summation notation, we're adding it to what would come out to be 19, and this comes out to 30. 36 minus 6 is 30. 49 minus 6 is 43. This is 58, and that would add up to 160. So this sigma notation adds up to 160. Here's an example of squaring the position. So we can use our rule of n plus 1, 2n plus 1, all over 6, using our formula from above. So our n term, in this case it's more like I, but it's going to be 28. 28 plus 1, 2 times 28 plus 1, all over 6. So we're going to take our 28 times 29, which is 28 plus 1. 2 times 28 plus 1 is 57, and divide that by 6. We get 46,284 divided by 6, which comes out to 7,714. The last idea here is graphing. When graphing terms in a sequence, the position is located on the horizontal axis. Which is our x-axis. Remember that terms in the sequence are discrete quantities. Therefore, we will not connect the dots together. So if this is the sequence that we're going to graph, our first term, second term, third term, fourth term, and fifth term, these are our x values. These would be considered our y values. 1 over, we go up to 2. 2 over, we go up to 4. 3 over, we go up to 6. Watch your scale, it's going up by 2s. 3 over, or 4 over, we go up to 8, and then to 10. We do not connect the dots because there is no value that's represented in between these terms. There is no 3, and we just connect them to show that it's a continuous path. There are no values in between, so it's considered discrete, and we do not draw a line connecting them.